still do.
Those gen chem classes are.
But the thing is, like, it's easier for me. It helps the professor as well as you guys, I hope, but it certainly helps me to, like, keep a track of, like, my notes. It's a very useful tool, I think. Okay, so let's pick up where we left off, which is just about ready for to do this. I think we'll finish this today. We might even have time to answer some questions. Today is Friday. Test is coming Friday. We're going to have, I think, an extra day. So we'll probably even have a day to probably do a review. So I'll confirm next week on that. So we left off last time, we started to dive into this whole question of what makes things magnetic. We know that rocks, right, some of these very early days, they could dig it right out of the ground, and if they had purified iron ore into iron metal, right, they went through that process of turning it into a metal, they found that some metals, like iron, stuck to it, whereas others didn't, right? Your gold wouldn't stick to this, but iron does. So ferrous metals. So back then, they didn't know exactly what the elements were. They just said, like, these things were ferrous, right? These things were not, right? Some things stuck to magnets, some things didn't. And we were talking about, well, why does this rock have a magnetic moment? Well, this rock is iron oxide, also called lodestone or magnetite. Iron oxide, there's like 3 or 4 different flavors of it, right? There's hematite, wolfstite, magnetite. Maybe there's just 3, right? So there's FeO, Fe2O3, Fe3O4, right? So it's just changing the oxidation state of iron. In this one, we decided that the oxidation state is actually mixed, right? There's 3 cations, 4 anions. You have to add up to a positive 8. Therefore, we must have +2 and +3 ions, right? So you've got a mixed oxidation state for your iron. And we basically said, like, oh, Fe3 plus, or Fe2 plus has 60 electrons, and those are probably going to be low spin in this structure, so no magnetic moment, right? They're going to go to the octahedral site and be uninteresting in terms of magnetic moment. But your Fe3 plus has 5 electrons. That's going to be where your magnetic moment comes from, right? So we gave the example of cobalt, the same thing. We talked about garnet, how it's a totally different crystal structure, and yet it's similar to the spinel structure, has 2 different sites on which you can get your magnetic moments occurring. There's 2/5 of those sites are octahedral, 3/5 of them are tetrahedral, right? So if you literally count this up, there should be more of these little blue tetrahedra than there are the purple octahedra. Maybe there are, right? So in this case, if you had Yig, yttrium, iron, garnet, Yig, then you have 5 irons total, and you've got 5 sites, right? 2 of them are octahedral, 2 or 3 are tetrahedral. So you just figure out how is that iron going to sit on those sites in terms of spin up, spin down, and I'll give you some tips on that. Once you know that, you can calculate what the magnetic moment would be. Let's do that for this one really quick. I don't think we actually did it. So if we assume that they are, I don't know if they're spin up or spin down though, or like high or low spin. So I don't have it written here. Maybe let me wait on that until I know for sure what they are before we work that
example.
example.
5 electrons, it wouldn't matter though, would it?
Well, they could.
Because you could feel, well,
It does matter if it's low or high spin, because what if, like on the tetrahedral site, it's probably going to be spin up because this is a small gap, so this is probably high spin. But what about on the octahedral? What if it's like that? That would change it. So I need to confirm that before I say more on that one. So we will do an example of garnet maybe on Monday. That's what. In fact, we'll do this homework problem 4 that we've decided to turn off. I will do this one in class. How about that? That work? Okay, we'll do that one. Turned off the homework problem. Okay, so we left off. Then we said, okay, let's talk about ferrites. Ferrites are enormously important, just like garnets, right? Ferrites are very important in class magnetic materials. And what's really powerful about ferrites is that they're tunable magnets, right? You can tune the composition, as we're going to work out right now, and you can get different magnetic moment per unit cell, right? So this is sometimes called crystal chemistry, right? You're talking about a crystal structure, but you're toying with the chemistry a little bit to get some property of interest, right? So let's go ahead and do this. We did it for the first one. We did it for this one. I want you guys to take your best bet on how do you get something close to the observed magnetic moment. You're going to have to make some guesses about what the spin states are going to be. So I want you to work these out for these remaining 5 problems, and I'll kind of help out. Okay, so let's do that now. If it helps, I can pull up a periodic table. Come on, internet. Going real slow. Okay, so we got our periodic table. Yeah, put that there. Okay. We'll put that there for the moment, right? So there gives you your ions, so you can count how many there are of each. It's just remotely easy to see. Kind of. Okay, take your best bet at what's going on there. What would the magnetic moment be? Remember, there's 2 of these for every one of these. Oh, is that the other way around? Let's see. Sorry, there's 2 octahedral sites and 1 tetrahedral site. Right? Getting a lot of blank looks. Should we do one together? Let's do, we did this last time. Let's do one more together this time, just to kick off today. Okay, so the first one where we left off last time, we did Fe3O4. Let's do cobalt Fe2O4, right? So what's showing you here is that you've got cobalt Fe2O4, and it tells you how do you get to the positive 8 with these ions. So it's telling you that on the tetrahedral site, it's completely occupied by iron 3+, right? We could look at our periodic table and decide how many electrons iron 3+ has. We say, all right, it's going to lose its 2 s electrons first. 1, 2, lose that one. That leaves 1, 2, 3, 4, 5 electrons, right? So Fe3+ is D5, right? So if you want, you can write it right here by it. 5 d electrons, right? Meanwhile, you've got Fe3+ over here. That's also going to be 5 d electrons. And you've got cobalt 2+. Well, how many electrons is cobalt 2+ going to have? Here's cobalt. It's going to lose these 2 first. 1, 2. That leaves 1, 2, 3, 4, 5, 6, 7. It's got 7 electrons, and it's on the octahedral site. So you have to take a guess now. What is it going to do on the octahedral site? Right, it's got 7 electrons. Well, it could either do one of 2 things. It can do 1, 2, 3, 4, 5, 6, 7, or it can do 1, 2, 3, 4, 5, 6, 7. Those are our 2 options, right, for cobalt 2+ on an octahedral site. You all agree? So which one is it? Well, in one case, you've got 3 electrons left over, and in one case, you've got 1, right? So overall, let's assume that Fe3+ is going to be all 5, so it's just unpaired for a moment. That's what we assumed previously. That means that the magnetic moment on your B site is going to be 5 plus either 3 or 1, right? So let's try 3 for a minute. If it's 3, then on your B site, you've got a total magnetic moment of 8, 5 plus 3. But remember, that means that you've got 8 pointing up, but the A site, there's one of those, it's aligned anti-parallel to it, so it's got 5 pointing down. So you're left over with 3. And in fact, you're pretty close to 3, right? So you know that this must be the favorable spin state for this ion, right? As opposed to this. Because if it was this, that would be 5 plus 1, and that would mean that your leftover spin is just 1. And we clearly have more than that. So this is actually a pretty good tool. If you can measure magnetic moment, it's a pretty good tool for estimating what your spin states must be. Right, Sherry?
We just always assume that iron's in the high spin state.
So this is tricky. On a homework or on a test, I'll make it clear. Yeah, I'll make it clear. Or I'll have to give you credit based on your assumption, whatever you assume, right? Because I don't think that you have enough information in this class to guess or have a good feel for what things ought to be. So I would grade it correct either way. Now I want to make my grading life easier, so I will try and tell you low spin or high spin, or like spin adds up to this number. Or I could give you something like, I could give you this exact question. I'd say, here's the observed value. As you tell me, what's the probable spin state? What's the probable spin state? Right? You do this the process exactly what we just did. You say, well, the only way to get anywhere close to 3 is if it's this. Fair enough? So why don't you do the next one?
Sorry,
yeah.
How did you go from the 5 plus 3 to 3?
Okay, so the trick to remember is that the moment on the A sites and the moment on the B sites are anti-aligned. They're pointing the opposite direction in spinels, right? Just like in garnet, these octahedral sites and tetrahedral sites are anti-aligned, right? Magnetic moments on the octahedral, tetrahedral sites are opposite in direction. Same way in spinels. So if you have leftover spin on the A and the B sites, right, they're going to be pointing in opposite directions. Therefore, your overall magnetic moment is going to be the sum of those two. You're going to have to subtract, I guess what do you call that? The subtractant? What do you call that? There's a word for it.
It would be a sum because it's negative.
Yeah, it's a sum, but one's negative. I like that, right? So that's all we're doing. We're saying -5 and +8, add it together, you get the +8. Fair enough? I saw some eye rolling from Chris.
Oh, no, because you said you add them together and you get +8.
Oh. Because math. Because 9:30 a.m. Right? You guys follow? So let's do the next one. You've got nickel iron spinel, right? Nickel ferrite, they would call this. Nickel iron oxide, right? It's telling you that the iron 3 plus wants to be on this tetrahedral site, but that you want a mixture of iron 2 plus and iron 3 plus and nickel 2 plus over here. So you have to first figure out how many d electrons will nickel have. We can do that. Nickel's right here, and it's nickel 2 plus, so it's going to have how many electrons? I think I count 8. So it's got 8 electrons, and on an octahedral site, where will 8 electrons want to go? And then what would the sum be? So nickel 2 plus, we said it's got 8 electrons. So technically you could put 1, 2, 3, 4, 5, 6, 7, 8.
Why is that possible?
Or you could do that. Well, it's possible. Is it ever going to happen? No. Just because it's possible doesn't mean that energetically there's a reason for it to happen, because these are at the same energy level, plus you paired it up. No benefit. Same energy level, unpaired. You get rid of that pairing energy. So this is definitely what's going to happen. So you've got 5 plus 2 over here. So you're going to have 2 magnetic moments, right? Which is pretty close to the observed value, right? So this is pretty slick. This is a nice tool for us to use. Why don't you guys do the next 3? Copper, by the way, is just 1 over from nickel. It's got 1 more electron.
There's only one.
I'm just getting this 5 plus 1 here, right? Therefore, a magnetic moment ought to be about 1, and in fact it is. Yeah,
So
Sherry.
we're predicting all these numbers, and they're all lower than the actual spin, the magnetic moment? Like, why is that?
So I would expect them to be actually the other way around. And I don't know if I can answer this without looking into it further. I can tell you why it tends to be lower more easily, because spins don't always line up exactly. They can be canted. You can have canted spins. And so like if the total length is like 2, but you're not along the same direction of measurement, then your like actual length is going to be 1.7 or something slightly less, right, depending on the angle you're at. Why it's larger, I'm not an expert. I'd have to look into
some
it.
irons that are in a low spin state, some that are.
I don't know offhand. It's a great question. I don't have a good answer for it right now. Barrett?
I'm more confused on magnesium.
Okay, what do you do here? Well, let's pull up magnesium. How many electrons does magnesium got?
The electrons for.
It's got it's got no electrons. It's magnesium 2 plus. Nothing.
Would we expect it to be? Yeah. So how?
So what'll it do?
Zero. Apparently it's 1.
You'd expect 0 though.
Yeah.
That's okay. You'd expect 0. I will not try and be tricky on the test. I will make this pretty obvious what's going on. What about this next one? Lithium. Lithium's 1 plus, so it's also got no electrons, right? You've got, but take a look at here. Now you've got different numbers, right? You must have to have 1.5 iron 3 plus ions and only 0.5 lithium. So does that change anything? I think you'd have 7.5. Right? Therefore, you'd expect 2.5. And you're pretty close to that, right? So this is ferrites, right? Magnetic moment in ferrites. Any questions on this? Could you do a test question on this?
Not the lithium.
I believe in you guys.
Not
I believe in you.
If it isn't tricky.
I'll probably give you a somewhat tricky one. I'll give you something like this. I'll say you've got ions that share occupancy on a site. So you're going to have to consider both of these, right? Just like you did here. Any questions? Did I clarify anything, Chris?
So on the very first one with manganese,
Yep.
you have like 0.2 and 0.8,
Okay.
but your number's 5.
The reason why is because manganese 2 plus and iron 3 plus both have 5 d electrons. They're both d5, so it's the same thing. Right, if you look at they're right next to each other. So manganese 2 plus, lose 1, 2, 3, 1, 2, 3, 4, 5. So it's got 5. But iron 3 plus 1, 2, 3, 1, 2, 3, 4, 5. So they're both D5. Okay? Yeah, Barrett?
Kind of a little thing on the question asked earlier. We were assuming a high spin for each of the, like for each instance of the activity.
In this instance, that's what we've been doing. I will make it clear on a test what spin state to assume, or I will give you enough information to calculate it.
Could it be that we're seeing higher actual measurements because some of the A sites are low spin?
For going low, yeah, that would actually do it. Right? Because these things, imagine these are like negative numbers. So if you have less of a negative number, that could be giving you slightly higher. That might be a reason. I don't know the reason for sure though, so I don't want to confirm that. That's a good hypothesis, right? That some of these are actually, but A site, you generally see things high spin on the A site, but maybe not all of them are. Maybe it's some fraction of them. I just don't know the answer to this one.
I was just super confused with why we were
Yeah.
doing anything.
That's a reasonable hypothesis. I just don't know the answer for sure. Chris?
Sorry, follow-up question. So for the magnetic moment on V for manganese, you wrote 5 plus 5. Shouldn't it be like 9 plus 1? Because of the 0.2? Yeah.
Say again? I lost you. So for this one,
Yeah, well,
why
so
isn't this
1.2?
9 plus 1?
Yeah.
Well, because
Well, it could be, but it's still be 10.
It'd still be 10, but it shouldn't.
oh, I see. Yeah, that should be. I see what you're saying. Because we're multiplying you're multiplying by the 0.2, you mean? Yeah, you probably should. I think I was being sloppy and I realized that these are both the same ion, so you're still getting 5 and 5 on average. But yeah, technically I should update that. Other questions on this? It's good? Crystal clear? Could you do it with garnets? How would it be different if I gave you a crystal structure with garnets? It'd be just like this homework problem. I'd say, in class we learned about the generic garnet crystal structure. We showed that Yig is ferrimagnetic. We'll talk about what ferrimagnetic means just right after this. Single crystals of garnets are valuable gemstones. You decide to use your MC degree to start a gem lab, which one of my students almost did. Actually, he was really pumped about this. You wonder if you can distinguish between colored glass and real garnets using magnetism. Right? Colored glass shouldn't be magnetic, but these might actually have a leftover magnetic moment, so they should respond like you should be able to pick them up with a magnet. Right? Actually, gem labs do this. What would be the magnetic moment per formula unit in demantoid, a green garnet gem with this formula? Assume that the iron is high spin 3+ and completely occupies octahedral sites. Calcium 2+ completely occupies dodecahedral sites. Silicon 4+ completely occupies tetrahedral sites. Should we do this now or should we wait till Monday? Should we just do it now? We're already working on it. How do you do this? How would you start this problem? It's exactly what we've just been doing with ferrites, but now it's garnet, different crystal structure. So the thing to remember is what?
What does the dodecahedral site look like?
Can I draw on this? I think you can, right? I don't know what it is. I don't know where. Can't remember how to draw on these things. And I can't get out. Close. It won't escape. How do I get out of this? Alright, there we go. How do we do this? What do you guys do? First off, what are the sites that we care about? There's dodecahedral, there's octahedral, tetrahedral, right? Well, what one of these has electrons left over, first off? Which one has electrons that might be even involved in magnetism? Do you have a question?
I do have a question.
Yeah.
So how do we know which sites are not to spin regarding each other?
That's what you'll need to just memorize for 2 crystal systems. For spinel, A and B are opposite. For garnet, octahedral and tetrahedral are opposite. That's all you need to know for this class. We'll talk about why they're opposite by the end of class today. Other questions? So how do you start this? Which one is even going to have electrons?
Iron.
Is it calcium or silicon? Nope. If you pull up the periodic table, calcium 2+, no electrons. Not going to be involved in the magnetic moment, so it doesn't matter where it goes. You can just ignore it. Silicon 1, 2, 3, 4. It's lost all of its electrons too, right? What?
It's minus. That's like
SI plus 4. So it's lost 4 electrons, right? So the only thing that's going to give you magnetic moment is your iron, right? And it's going to have its iron 3+, so it loses 1, 2, 3. That leaves 1, 2, 3, 4, 5 electrons. So it's got 5d electrons. I think we tell you in the problem it's high spin. It's high spin, and we tell you where it sits. It says it completely occupies octahedral sites, right? So per formula unit, how many octahedral sites were there again? If you don't remember, you want to put something like this on your note sheet, but there are 2 of the 5 that are octahedral. 2/5 of them are on octahedral sites. 3/5 are tetrahedral. So per formula unit, which is this thing, you're going to have 2 sites that are octahedral. Each of them is going to have 5 magnetic moments. So you would expect what magnetic moment per formula unit? 10. And then do I ask per formula unit or per unit cell? Yeah, per formula unit. So it'd be you'd expect 10 Bohr magnetons per formula unit, right? So could you pick this up with a magnet? Yeah, you betcha. You should be able to pick it up with a magnet.
Does it have to be a strong magnet? Or just-
I don't know if I can answer that question. I don't know enough about magnetism. I would have to consult my book. I don't think so. I think that this would be a decent magnet. Right? And 10 Bohr magnetons per formula unit. It would depend on how many formula units there are per unit cell and all that, but I think that this would be a decent magnet. Any questions on this? Yeah.
So you're finding equations of like magnetic moment equals the square root of the number of unpaired electrons times 2 plus the number of electrons squared. Are we just saying that each unpaired electron creates its own magnetic moment?
Each unpaired electron has a Bohr, it has a Bohr magnetism, Bohr magneton, 1 Bohr magneton of magnitude. Right? Yeah. Any questions on this? This straightforward? If I gave you slightly different, I said something that now silicon had leftover electrons, right? A different ion instead of silicon that had leftover electrons, how would you do it differently? What if you had, whatever it was, had 1 leftover electron on that site? How would that change this question? What would the value then be?
You have to. Plus.
Maybe turn to your neighbor. As much as I love Barrett answering all of our questions, I want to spread the wealth a little bit. Turn to your neighbor and tell them how you'd solve this. The question is, exact same question, except instead of silicon here, you had some ion that had 1 d electron left over. How does that change our answer?
So would that still be a 3 there?
There's still 3 of them, but now it has a D1 configuration.
The other
Calcium's the same, iron's the same. So same occupancy, right? Iron's still in the octahedral site. Whatever this is, we're going to find out what this ion is in a moment. We'll call it atom X for right now. Atom X has 1 d electron. It's on the tetrahedral site. What's your magnetism per formula unit? You got a guess, Barrett? Or you got a question?
Just really quickly, which one's minus which one?
Which one? Say again?
Which site is minus which site?
Octahedral and tetrahedral are anti-aligned, meaning one is positive, one is negative.
So it doesn't matter.
You can define it however you want.
Just take the magnitude. Right?
Yes, it's the magnitude. Okay, what's our answer?
7.
Yeah, it was 10 before, and now those 10 were all pointing the same direction, right? You had 5 and 5, and then now you've got 3 sitting on the 3, right? 1 each for each of the 3 tetrahedral sites, pointing the other way. So you'd have 7, right? Now, next question: what ion would that be? What ion could potentially give that scenario? That gives you +1 electrons. Remember, it's got to have the same charge as silicon because charge is to balance.
Phosphorus 4+.
Phosphorus 4+, right? That would have 1 unpaired electron, for example. I guess that would work. What else would work? How about vanadium 4+? Right? Vanadium 4+ loses 1, 2, 3, 4. It's got 1 left over. Or chromium 5+. Manganese 6+, right? Any of those things would fit it, right? Plus, when you go to higher and higher oxidation states, your ion's getting smaller and smaller, and it's a tetrahedral site. That's a small site. So that might actually exist. I have no idea if it really does, but that's the right kind of thinking, I think, towards a problem like this. Okay, we good? Should we move on? Let's keep going. By the way, if you came in late, we ditched this problem. We're not going to do it. So you don't have to do it no more. Please do it in class. All right, so magnetic moment in materials is the same as dielectrics. Dielectrics, we said, okay, you've got regions of polarization where you've got like slight positive, slight negative, slight positive, slight negative, right? These things line up. Now we have the same sort of thing happening, but instead of polarization, you've got magnetic moment. You've got regions where you've got unpaired electrons, all electrons pointing in one direction, right? your overall magnetic moment, which is right these spins, leftover spins, they're all pointing the same direction if it's in an externally applied magnetic field. Before it was an externally applied electric field that lined up your dipoles. Now a magnetic field will line up your magnetic dipoles. They're not called dipoles, magnetic domains, we should call them. Right? It's completely analogous. Right? One was called a ferroelectric. That was for our dielectrics. These are called ferromagnetic. We said there's another one, ferroelastic. What was ferroelastic again? Jason's got an idea, but he's not committing to it.
No.
What is it?
Well, it's just where the atoms can slightly move in structure.
They can shift. It's a strain, right? So ferroelectric is dipoles, ferromagnetic is magnetic moment, ferroelastic is elastic, right, strain, right? Meaning here we used an electric field to create dipole alignment. We used a magnetic field to get magnetic dipole moment. How do we align strain? Yeah, you apply stress. You apply a stress, right? And that's gonna be your field, if you will, your stress, right? Any questions on this? So these are all just they're the exact same thing. That's why they have ferro in their first part of their name. They're very, very similar concept, right? So just like so here's a comparison: magnetization versus polarization. At the Curie temperature, you get spontaneous magnetization if you go below it, right? Same thing, if you go below the Curie temperature, you get spontaneous polarization. If you go above the Curie temperature, you're giving it too much thermal energy, and these things want to be like, there's too much energy for them to be all aligned, so they just split. It's like everyone in this class. I think we gave the example, if you close your eyes and I say point your arm in any direction, when you guys open your eyes, everyone's pointing a different direction. That's what happens above the Curie temperature. You got too much thermal energy, so on average, they're just pointing every which way. They're not aligned even in domains, right? You've got ferromagnetic as opposed to ferroelectric. You've got paramagnetic versus paraelectric. What was paraelectric again? It's the state that I just finished describing. Paraelectric, when you go above the Curie temperature, every dipole basically switches to whatever direction you want, right? There's too much thermal energy, and overall, these all just cancel out. It's paraelectric, so it's totally random, which means that the overall magnitude just goes to zero. Same thing with paramagnetic. If you go above the temperature at which these things are, they've got too much thermal energy, and these things align in every which way, it becomes paramagnetic. This happens, by the way, with magnets. If you saw my iron wire demo in 2010, we've got that wire, we stuck a magnet to it, and when you heat this up above the temperature, when you go ferromagnetic to paramagnetic, the magnet falls off, right? Which is pretty slick, right? You've got antiferromagnetism versus antiferroelectric. What does that mean? Antiferromagnetism means that you've got maybe like 5 up and 5 down. So overall, there's no net magnetic moment. Or in a ferroelectric, you've got 5 charges pointing up and 5 charges going the other way, like 5 positive, 5 negative, right? Overall, no net dipole, right? They cancel out. If they perfectly cancel out, we call that antiferromagnetism, antiferroelectric, antiferroelastic. I haven't heard of. I'm sure it's out there. I'm sure that somewhere that exists. I don't know it, right? And then you've got magnetic field doing the aligning, electric field doing the aligning. We could do another column for elastic, right? For all these same things. So let's talk about why antiferromagnetism is so common and why so many compounds are anti-aligned, right? Why do you get tetrahedrals point that way, then octahedrals have to point this way? Where's that coming from? It comes from something called superexchange. Superexchange can be described as follows. It says, when magnetic dipole exists, it's canceled out by an opposite direction magnetic dipole. So imagine for a moment you've got 3 atoms, right? You've got manganese ion, manganese 3+, it should have 5 d electrons. 4? Did I do the math wrong? Maybe it's 4. Manganese, is it 3+? 1, 2, 3. Okay, yeah, it's got 4. Sorry. So you got manganese 3+ that has 4 electrons, right? 1, 2, 3, 4, right? We haven't drawn these in our normal way of thinking, like the 3 low, 2 high, right? We can do that if you want in a moment, right? But it's got 4 electrons somewhere in its d orbitals. You've got an oxygen. That's p, not d orbitals, right? It's in its p shell, so it's got its p. And then you've got this manganese 3+, right? So why are these ones pointing up and these ones pointing down? It has to do with the fact that this is a bond right here, right? That's a covalent bond, right? This is a bond right here, it's a covalent bond. Meaning these things, the only way that they're satisfied is by sharing, right? And so in one orbital, in one bond, you can only have 1 up and 1 down, right? In that bond where it's formed right there, that's like one of these, it's sharing it. And you have to, at best, do that. Therefore, if this one is up, that requires that one to point down. right? This one is pointing up. That requires that this one point down, right? So this is super exchange. That's why if you ever have an ion linearly bonded to another transition metal ion with like an oxygen in the middle, it's very common to get anti-alignment in those things. So in the garnet crystal structure, you've got octahedral and tetrahedral sites. Let's go back to it. I don't know if this is going to be easy to see or not. Basically, they must have like linear arrangements, and they kind of do, right? This kind of looks linear. I don't know if that's the right one to look at, but you can see that like you've got an ion here. This is actually bent, right? Imagine this was a straight line here for a moment, like that it wasn't bent. Then you'd have transition metal, oxygen, transition metal, right? And so these things would have to be anti-aligned according to superexchange. In this drawing, I don't know if that's a great way to think of it, but that's the concept behind this. Okay? Any questions on superexchange? What's causing that? I think they just show it in different organizations here. That you can get, so here they've got D, this looks like the dxy level, or x squared minus y squared, and another D orbital there. And I'm not going to go into greater detail than this. I think Tawari teaches a class where he gets into magnetism if you are interested more in this. For now, I think it's enough to say that superexchange occurs because this is a bond, and in a single orbital you have to have one up, one down, and so it leads to this exchange principle, right? Any questions on superexchange and how that leads to antiferromagnetism? What's happening with B?
Because there's like an additional arrow in there.
Well, it's telling you that this electron is occupying a different state, basically. So basically, this is not a bond, is what that's saying.
Oh.
These are not bonding, because normally when you do like the HOMO-LUMO diagrams, right, when you do like, you do this, right? These come together and they form like your two antibonding, you got bonding levels like that. It's basically saying instead of sharing a level, which it could go down in energy to share, you're choosing to put one at a higher energy level. This thing's going up rather than sharing here, right? This would be lower energy, but if you put that one up there, that allows you to stay up and up, right? I think that's what they're getting at there. I didn't make this drawing. I stole it from the interwebs. Okay, questions? Superexchange, magnetism. I think we're about done with this. Any questions? Okay, let's say a few brief words on optical properties. Oh, sorry, one more thing here. Ferrimagnetism. We mentioned that word. So there's ferromagnetism and then ferrimagnetism. What's the difference? Well, it means that you still got like your opposite dipoles, but maybe you've got 5 pointing up and like 3 pointing down. So overall you've got left over 2. That would be a ferrimagnetic material. Ferromagnetic means they're all pointing the same direction, right? With however many dipoles. Antiferromagnetic means they're perfectly anti-aligned, so there's no magnetic moment. And ferrimagnetic, which is going to be the most common one, right? You've got some pointing down, but more pointing up, right? So you have something left over. So you've got ferromagnet, antiferromagnet, ferrimagnet, then I don't know what that is. I don't know if that's anything.
Wait, wouldn't E be ferry and D be something else because the dipoles are different strengths?
That's the point, right? Ferrimagnetism is one is stronger than the other. I guess this would be a type of ferrimagnet if they're the same. Let's see, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. If it was that there's more of these pointing down, this would still be a ferrimagnet. Okay, just like electric domains, you can have hard and soft hysteresis loops, right? Hysteresis, that's an important word to remember. Hysteresis is just anything that when you apply, say, for example, if we're talking about applied magnetic field, you apply a field and that creates this magnetization. You can't just infinitely magnetize it. You can only align the dipoles so much. So basically, you're applying more and more field, you're getting diminishing returns. It's not getting any better. Then you switch the field, you're going to go back in terms of field. That causes this to switch down here to get diminishing returns. And you can switch this over and over, right? So this big loop means that you have lots of leftover magnetization, even when you put the field back to zero. We call that, again, remanent. Did I say that? Yeah, it's called remanent instead of remnant. I don't know why they call it that, but remanent magnetization. This would be a hard magnet, a very soft magnet, sort of in between. So if you have a material, when you take away the field, right, if you take that field back down to zero, and there's not much magnetization left over, it's a soft magnet, right? So like the neodymium magnets that are like give you blood blisters that catch your finger, these are really hard magnets, right? The things on your fridge, generally softer magnets, right? And both of these have sort of different applications. Not that one's better than the other. Like one's a stronger magnetic field, but they have different uses. You can use soft magnets, hard magnets for different things. Yeah? I'm going to skip permeability. So soft ferrites are typically spinels, right? So the ferrites we talked about, like the nickel iron oxide, those spinel ones, those tend to be soft, whereas hard ones can be like barium iron oxide. This is no longer the spinel crystal structure, it's a different one, also super common. So what would square loop ferrites be good for? Something that can switch easy but keep its magnetic moment would be like computer storage. You want to be able to switch it easy, but you don't want to lose the magnetic moment, right? We'll skip that. Okay. And just like you could with dielectrics, where if you went from above the Curie temperature to below with an applied electric field, if you do the same thing with magnets, if you go from above the Curie temperature, there's actually other words for this. There's something called the Néel temperature. But think of it in the same way. Above the temperature where it's disordered to below, if you have a magnetic field applied during that, then you can pull them and make them stronger, just like with electrics. Right? All right, let's talk about optical behavior. What do we care about in optical behavior? Do we care about optical ceramics? Are they good for anything? You can make things that look pretty. Like, that's clearly nice, right? You can make an industry out of that, I guess. Are they technologically important? What do you think?
Can you use them as filters?
Yeah, absolutely. You could use it for filters. What else could you use these for? Do they have any technical implication? Optical ceramics?
Lasers?
How light works? Yeah, lasers is going to be a huge one. Where do we use lasers? Everywhere nowadays. They are insanely important technological advancement. They only work because of optical ceramics. We'll get to in a moment. Anything else? What else do we care about optical ceramics? Anybody have fiber internet? That's the bomb, right? That's terrific. How does it work? How does fiber internet work? Instead of communicating electrons, you're doing light, which is super fast, right? How does it work? If you're sending light and that's your means of communication, right, to check your email, how's that actually working? You have to have a way for light to travel from wherever your internet service provider's at, clear out to wherever you live, right? So there could be turns, there could be like ups and downs. Like, how would you actually transmit light there? You clearly don't have line of sight everywhere. So they have what? Fiber optics, right? Fiber optic cables is something that when you send light into this little cable, which is a glass ceramic, it stays in there, even though the cable's doing whatever this thing, pretty magically. It sounds magic. The light, which we think of as traveling straight lines or bouncing off of things, right? It stays in that cable and doesn't get out, right? We'll talk about why that is, hopefully, in 12 minutes, right? So let's begin. Optical behavior. First off, there's color, clearly. There's index of refraction. There's absorption, transmission, phosphorescence. All of these things have important technological applications, every single one of them, right? And basically, when you're talking about optical properties, you can't separate that you're dealing with electromagnetic radiation. That is light, right? Optical means dealing with some sort of light interaction. So you're going to have to be dealing with how your material interacts with electromagnetic radiation in different ways, right? So first off, let's talk about absorption and transparency. Some things will intrinsically be transparent. You don't have to dope it or do anything to it. It'll just be transparent, right? Glass, when you make glass, you don't have to dope it very much, and it'll be transparent, right? If you want to change its color, like in our glass lab in 2010, I think we added different dopants to the mostly borosilicate glass. So you start out with a borosilicate, B2O3, a little bit of SiO2, you add some other stuff, lime actually, and then we added other things to change the color. What's actually going on, you think? What's happening when you add dopants to change the color? The answer is right there if you want. Right? Radiation promotes an electron from an initial energy level to energy levels that are higher up, right? Then as that drops back down, you're getting transmission of light, right? At a specific wavelength, so a specific color, right? So if you put in ions like cobalt oxide, what you're really doing is every single one of those cobalt ions is now a color center. It's a center which has electrons occupying, right, some energy level, right? You got electrons here. In comes a wave of light from whatever you're looking at, right? That's going to bump this thing up to some higher energy level. And when it comes back down, this is a very specific delta E, change in energy, and therefore it's going to give a very specific wavelength. Right? A very specific wavelength where you know that E equals HC over lambda, right? So this is a color center that gives you the color that you're interested in. Yeah, Barrett?
Basically, when we're looking at something that is the colored glass, what we're seeing is just tons and tons of electron energy transfers.
Yeah, and it can be a little more than that. Like, what if What if you're absorbing, we're going to do an example of this. What if you have a band gap in the material, right? So you've got, not just a single lone thing. What if like all your material, right? So this is like dopant scenario. You could have your bulk material where you've got a band gap. Well, what will happen is you shine light on that with higher energy than your band gap. Some of that's going to get absorbed and some isn't, right? So the stuff that get absorbed, right? If I've got a sheet of this stuff, the stuff that gets absorbed doesn't make it to my eyes. Everything else does. So you've blocked out one color, right? So let's do that example actually right now. Got it right here, right? Recall that one wavelength is absorbed, then you're going to see the complementary color, right? Right, the combined result for the other ones, it's called the complementary color, right? So cadmium sulfide, so it says the band gap is 2.45 electron volts. What wavelength does that light correspond to? So E, how did you know it's blue? You did that quickly though? Like how did you know that was blue? This isn't listed in EV here, this isn't given wavelength. So you could calculate, plug that in, this is all constants, you can calculate that, and you should get a value. How did you know it was blue though? Who did? Oh, because Cohen.
Yeah, because Cohen.
Why is it blue? Because Cohen.
Yeah.
Fair enough. I'll accept that as an answer on the final exam. Because Cohen.
You've taken this class.
I've been there. That's a hard class. Okay, what do you think,
That's
Chris?
pretty easy short color. You just do 1250 divided by the band gap.
Yeah, no, for sure. By math, we can do this. But somebody said blue, and I was hoping that there's another trick. This is cadmium sulfide, right? This is the material we're talking about. How did you know that the band gap is in the blue? Because you see orange. You see the complementary color. Do we have the color wheel here? Let's pull it up. Complementary color wheel. Yeah, like this thing. If we see it and it's kind of this orangish yellowish thing, that means that we must be absorbing somewhere around here. This is getting absorbed, so the other light's getting through will make it look like that, right? Which is pretty clever. Which is why blue and orange look good together. By the way, when you're designing posters and stuff, complementary colors. It's the way to go, right? Take a little bit of this, a little bit of that, you're in business. A little bit of this, a little bit of that, complementary colors. Yeah, I agree. That's actually not a good way to go.
That's the one you can't do. That's why
Do other ones. Other ones look nice. I promise. Especially blue and orange. Blue and orange look great. Okay? That's a free tip. That's a tuition-free tip. Your tuition is, we're stretching it. We're getting all the value you can out of this class. Right? Okay, so there's intrinsic versus extrinsic. Extrinsic is when you dope it with something. You put something in intentionally to change the color. That's like the cobalt in the glass, right? Or the iron oxide. They put chromium in glass because chromium makes it turn green, right? So there you're adding in something that specifically is changing as opposed to the intrinsic properties like the band gap. Okay? You can make ceramics that are almost entirely transparent. This is shocking, right? Most ceramics you think of as like a chalkboard or like chalk, like you're not seeing through that. Why do you not see through it? Almost always the problem why you don't see them, it doesn't have to do with intrinsically that it's absorbing the light. Sometimes that's the reason. It's usually because of pores, right? You'd have to get rid of every tiny pore because a pore is going to scatter light. It could scatter it so much that the light never even gets through, right? So, but you can make ceramics that are transparent. The trick, if you want to make it look more transparent, just set it right on top of something. If you hold that an inch away, actually, it looks much worse, right? So Dr. Shetty has done a lot of this work in our department. He's actually very expert in optical properties of ceramics. And getting rid of that porosity is non-trivial. It's really, really tough. And you not only need to get rid of the porosity, but you need to keep the grain size small. If the grains grow like crazy as you're getting rid of the porosity, which we'll learn about starting next week as we dive into processing, it won't work either because then big grain boundaries scatter light. Yeah.
So with larger grains, you get bigger grain boundaries.
Or, sorry, not big grain boundaries. Larger grains scatter light. This is not the grain boundaries.
Oh.
It's the size of these grains. Small grains. So if you make YSD or alumina really, really dense, so you got rid of all the porosity, and you're somehow able to keep the grain size small, that's a tall order. We'll talk about why that's so tough later this semester. You can make them transparent, right? So why do you want transparent? Well, because you can do cool things with it, right? You guys have seen these probably close to at least once a week in your entire life. What are these? I said it. It looks like a what?
Don't they filter out UV light?
I don't know if they do that or not. They might.
It's like
This is the orange one.
But you guys use these all the time. You just don't realize it.
LCDs or something?
They're what?
Are they LCD screens?
No, these are good guesses. You'll be shocked. This is a checkout counter at a grocery store. Why? What is this, right?
Oh, that's the laser.
The laser thing is underneath there. It needs to read barcodes, right? So you need something transparent, but you're going to be swiping stuff across it hundreds of thousands of times. I don't know. I don't know what the lifetime expectancy of those little booths is. You want it to last a long time. Every time it gets scratched, that's going to be a real problem. So they use ruby or something like it. I think these are actually like sapphire, right? They make thin, very scratch-resistant ceramics, a very hard scratch-resistant ceramic that allows, I don't think it's actually ruby, it's probably some variant thereof, right? But that's the idea behind it. You could put them on radar missiles though, right? The domes of missiles, radar domes we call these. Not super wonderful way to think about it, but technologically important, right? How does a heat-seeking missile work? Actually, Cohen taught me this. Of course he did. How does a heat-seeking missile work? You've got a grid of sensors, 9 sensors. Basically, you've got the engine, your airplane, or whatever you're trying to shoot down that has a heat signal. So you have something that can detect heat signal, detects the radiation from it. And if it's mostly over here, then you steer your thing until it's in the middle. If it moves down here, then you steer your thing until it's back again in the middle. So you have to have at the front of your missile something that's transparent to radiation if you're going to build this device. Enough said? Enough said on missiles.
Yeah.
Right?
He probably see really interesting things in that class.
He's a smart guy. Let's skip that. We got 3 minutes left. Let me skip most of this. Phosphorescence is important. Basically, phosphorescence is a process where you go from up to here, like you promote something and it's going to drop back down. Normally, all we care about is this change in energy. What this cares about is the time. Like, how fast does that happen? Does it happen immediately? Does that rate at which it drops down depend on temperature? In fact, it does. So here's your decay time in microseconds as a function of temperature for a bunch of these different phosphors. So this was from my PhD advisor's work. I didn't work on this. One of the other guys in my lab did. Where basically you can make temperature sensors by embedding maybe different parts of these materials in your whatever you're trying to measure temperature of optically. So you make a ceramic and you put in a little bit of dopant of whatever this is, right? You can then pulse it with a laser and then look at the decay of the light coming off, right, with another sensor. And if you look at its the time, it'll depend on the temperature, right? So if it decays really, really fast, you must be at a higher temperature. If it decays slowly, like this decay lifetime is slower, then you know you're at a different temperature. So it's a really interesting way to measure thermometry at regions where maybe you can't just stick a thermometer. Like how, for example, what he used it for was in turbine engines. You'd like to be able to monitor the hot side region of that turbine blade that's spinning thousands of times per second, right? But you can't just like stick a thermometer on there. And yet you need to know how hot it is because you don't want to run too hot or it'll cause massive problems. So this is a non-contact, easy way. You can pulse it with a laser, measure the decay lifetime coming off. Lasers, you know, let's just do this right. We'll spend 5 more minutes on this next class. We'll wrap up here. Any questions? Questions? Ceramics, magnetism, they're all experts. Feeling good about it? Ready for the exam? Okay. I'll try and post the study guide this weekend sometime so you have a few days to look it over. And again, we'll do a review session. I don't remember what day we're doing it. Let me tell you. Was it Wednesday? Okay, Wednesday night we're doing the review.